All right, so now we need to talk about something called linearization, tangent planes, and normal lines. This shouldn't say normal planes. That should say normal lines. Okay? So, this concept is fairly similar to this concept that we've looked at back in Calc 1, where you talked about linearization of a function of a single variable and the tangent line to the curve. We're just now expanding it into 3 dimensions, so we're talking about linearization of a multivariable function and the tangent plane. So first, let's just talk general concept. So let's look at this picture here. This concept of linearization of a surface is very similar to the idea where people thought the Earth was flat. You look at this blue surface and you clearly see that the surface is curved. Okay, you can think of that as, part of the Earth's surface. It looks like it's a sort of a component of the sphere, right? So let's look at that blue surface. Clearly it's curved. Clearly it is not flat. It is not a plane. However, if I'm right here, if I'm standing right here at that point, or if I was to zoom in really, really close to that point, it would look as if that surface where I'm standing is flat. Okay? And so if I look at these two things, this plane at that point, okay, this plane at this location and this surface at this location, clearly they are very different, right? I'm zoomed out here now. You can see we're zoomed out. You can see it. They're very, very different things. But if I was a little microscopic being here at this little point, I really wouldn't be able to tell the difference between that tangent plane and that surface. Or I shouldn't say tangent plane yet. That plane and that surface. And this is the whole idea why people thought that the Earth was flat, many, many years ago. Unfortunately, some people still do think the Earth is flat. We're not going to get into that. Anyway, because when you're up close, a curved surface seems very similar to a plane. And so this is the concept of the linearization of a function or a surface, and then it gets us into tangent planes, and then we can also talk about normal lines. All right. So let's go into some Calc 1 real quick. Linearization for a function in Calc 1. So you have a curve, okay, some random curve here, and you're at this random point on the curve, you can find the tangent line to the curve at that location. So this is the tangent line. This is the function. All right. Clearly, they are very different things, right? They are very, very different things. You can see that they are very different things. However, if I look really, really close, if I zoomed in real close here, I want to be able to tell the difference between the tangent line and the function at that specific location. Why not? Well, the point that I'm standing at, the x and the f of x, those coordinates are the same on the line and on the function. So the x and the y basically are exactly the same in both locations. Whether I'm on the line or I'm on the function, I'm at the same spot. Also, the rate of change, the slope right there, is exactly the same whether I'm on this line or whether I'm on this curve at that specific location. So everything about this point on this line and this function is exactly the same at that location. So I can't tell the difference between the tangent line and the function here. As I move away from that point, you start to see there's a difference, right? There's a clear difference as I move further and further away from that point. The y values are changing. This y value is different than this y value. The slope here is different than the slope here, okay? But at this location here, they're very similar. And so that's the concept of, again, the linearization of a function, in that this function can be replaced with this line at this location. And even if I moved away from that point, so let's zoom in a little bit here to just this curve. Here's the point. Here's the tangent line, okay? Even if I was to move a little bit away from that point, there's a difference, but the difference is small. The slope difference between this point and this point is not that much. The y values don't differ by that much. And if I go a little bit further away, All right, they're going to be a little bit further from each other. The y values are going to be a little bit different. The slopes are going to be a little bit different, but not a whole lot from what was here. And so what I can do is I can say, well, yeah, right here, the tangent line and the curve are identical to each other. And if I just go close to it, so let's just say in this little vicinity here, the tangent line and the curve are relatively close to each other, in which case they should be interchanged with one another, barring a minor amount of error. And again, this is what we talk about the linearization. So then if I just am talking about the function, okay, here's the function. If I'm just working with this function, but rather than working with the function over its entire domain, I'm only looking at the function in this little mini interval, then I could replace this function with this tangent line and not get much of a difference in any of my calculations. So where's the benefit here? Well, the benefit is that if this function is fairly complicated over its entire domain, but I only need to work with that function in this little location here, then I can replace it with just this linear function, this line, and I can get generally a lot of the same values or similar values in my calculations than if I worked with a fairly complicated function. And we do this all the time. When there's a very complicated calculation that needs to be done, but it only needs to be done in a very small interval, we can replace a function with a line, specifically its tangent line, at that location to make our calculation easier. Now, we'll have a little bit of an error because the line and the function, once we move away from that specific point, aren't quite the same. But that error might be worth it to not have to have such a complicated calculation. All right. So the linearization is basically the equation of the tangent line. So it goes like this. It says, all right, let's look at the slope of the tangent line, right? Or let's say the equation of the tangent line. So we have this function f of x. All right, that's the function that we're trying to linearize. We could find the derivative of that function at a. We could find the y value at a as well. So we have this point a comma f of a, and the derivative is the slope of the tangent line. All right. So if I use these two components, I could write the equation of the tangent line by doing y minus y1 times m, which is the derivative, times x minus x1. Okay, just use your point slope formula. In which case I could solve for y, and I could say f prime of a equals, or f prime of a times x minus a plus f of a. Right? And that would be the equation of my tangent line. That's the tangent line to f of x. Remember, f of x and y are the same thing, right? So what I can do is I can replace y with f of x. But what does that look like? Well, what that is essentially saying that f of x equals this. So this is your linearization for your function. That the function f of x and this function, which is the equation of the tangent line, the tangent line itself, they are equal to each other at, well, let's get a color you can see, at a f of a. And when I move away from that point, just slightly, this function can be estimated by the tangent line. But anyway, that was what you call the linearization for a function in Calc 1. And so we use that same idea to really do the linearization for a multivariable function in Calc 3. So here a continuous function f of xy is differentiable if it is locally linear. That is, if the graph looks flatter and flatter as we zoom in at one point. So this point a, b, f of a, b eventually becomes indistinguishable from the tangent plane. That's what we just talked about. Okay? When you zoom in, you can't see a difference. So, if a tangent plane to z at point P, AB, f of AB, exists, then its equation must be the linearization of z. Okay, that's what its equation must be. It must be the flattened out version of z, where L is this linearization. So how do we get that? Well, we basically get it the same way. If the linearization in 2 dimensions was f prime at a, was the derivative at a times x minus a plus f of a, which was the y value, then we just extend that to our multivariable concept, and we have this derivative times x minus a, which is essentially this, but it's derivative with respect to x. Plus, we also have a derivative with respect to y, and y minus b, plus the function value. Well, the function value is now f of ab instead of just f of a. And so what we get is that the linearization for a multivariable function is found using this formula, which is just an extension of the linearization in Calc 1. And so if I said, all right, let's find the linearization for this function here at this point, what are we doing? Well, what we're doing here is we are applying these pieces here. This is A, B. Okay? We need to find f of x. We need to find f of y. I need to be able to write. That would be key. So there we go. All right. So f of x, derivative with respect to x would be 2xy. Derivative with respect to y would be x squared plus 6y squared. We also need to find the derivative with respect to x at AB. Derivative with respect to y at AB. So at this particular location, we need to know the specific derivatives, the slopes in either direction at that specific point. And so that would be what, -4, and f of y with to -1 would be, this would be 4, this would be 6, so 10. And we also need to find just flat out f of ab. We don't know the z value, right? We need the z coordinate, the f of ab here. So it'd be the f of 2, -1. And that would be, what, 4 times -1 would be -4 plus -2, so what's that, -6. So there's that. So if we plug all that in, this goes here, this goes here, this goes here, and then a and b, what do I get? We get that the linearization for this function should be -6 plus -4, so I'll just write -4, times x minus 2 plus 10 times y minus 1, so y minus -1, so plus 1. And there's your linearization. That's the linearization for the function f of xy. So the idea here is, again, clearing this up a little bit, at this location, this function and this function behave exactly the same. There is no difference between this plane and this function at this location. As I move away from this point here, there starts to become a difference between this function and this plane. But it's a minor difference. The further I move away, the bigger the difference would be. But at this location, this function and this plane are identical. So I could swap one out for the other and not really notice a difference. And therefore, this is the equation of the tangent plane. If you see that, we can show that real quick. Remember, if we say this is a function z, z equals -6 minus 4 times x minus 2 plus 10 times y plus 1. Distribute this out, give myself some room. I'll put it up here. What am I going to get? I'm going to get z equals -6 minus 4x plus 8 plus 10y plus 10. Bring all my x's and y's to the left. So I get 4x minus 10y plus z equals negative 6 plus 8 is 2 plus 10 is 12. I get that. You should notice that as the equation of a plane, right? That is the exact formula for the general form of a plane. So this is a plane, right? This is the equation of a plane, specifically the tangent plane. And the tangent plane is the linearization for a surface in two variables. So as we left off, the equation of the tangent plane is given by the linearization of the function. In this case, this is our equation of our tangent plane. So if I said find the linearization of a function, or if I said calculate the tangent plane to the function, really asking you to do the same thing. So again, that would be, finding this plane that's tangent to the curve right here. And, the idea is that it contains the two tangent lines parallel to the x-axis and parallel to the y-axis. So here we have a question that asks us to find the equation of the tangent plane to this function at this location. So basically what that picture just described, now we want to actually calculate the equation of that tangent plane. And so we're going to need a couple of things. We're going to need f of 4, 4. We're going to need the partial derivative with respect to x. We're going to need the partial derivative with respect to x at 4, 4. We're going to need the partial derivative with respect to y. And the partial derivative with respect to y at 4, 4. Okay. So all should be pretty easy to find. F of 4, 4 would be 4 over square root of 4, so 4 over 2, so 2. The partial derivative with respect to x would just be 1 over square root of y. At 4, 4, that would be 1 over the square root of 2. Sorry, 1 over the square root of 4, which would be 1 over 2. The partial derivative with respect to y would be x times minus 1 half y to the minus 3 halves. I could write that as negative x over 2 y to the 3 halves. That's just power rule. I would bring this up to the top, right, as a minus 1 half power. So y to the minus 1 half, and then I could take the derivative that way. Plug in 4, 4, I get negative 4 over 2, 4 to the 3 halves. 4 to the 3 halves is square root of 4, which is 2. 2 cubed is 8. 8 times 2 is 16. So then this will give me negative 1/4. Okay. So now that I have this, this, and this, I can find the equation of the tangent plane as z equals f of 4, 4, which would be 2, plus the partial derivative with respect to x at 4, 4, which is a half, times x minus 4, that's the x value here, plus the partial derivative with respect to y, which would be negative 1/4, times y minus 4, again, that's the y value here. And so that would be the equation of the tangent plane. We usually don't write the equation of the plane like that. I mean, typically we use the standard form. So I would multiply this in here and here. So I would have z equals 2 plus a half x plus 2 minus a fourth y plus 1. Group all my x's and y's together, so I can just dump everything over to the left-hand side. So minus 1/2 x plus 1/4 y plus z equals 2 plus 2 plus 1, so 5. So that's most likely the way you would see the equation of the plane written. So there's your tangent plane to this function at this point. Now, writing the equation of a tangent plane, or linearization, is all well and good when those functions are explicit functions. But surfaces aren't always given in the explicit form, which is this form here. Sometimes surfaces are given in the implicit form. And so we need to talk about notation for implicit functions. So first let's talk about single variable. We know that y equals f of x. So they're interchangeable, right? We use y, we use f of x, but we can say y equals f of x. Y equals this function of x. Okay? Then what I can do is I can move this y to the other side of the equation by subtracting it, in which case this is 0, and now I have f of x minus y. And now it's no longer explicitly solved for y. Okay? It's not y equals. This is an explicit equation, and this is now implicit. Now we haven't talked about implicit differentiation yet. We don't need to, but the notation for an implicit function can be written in this way, in that if you look, this has both x's and y's on this side of the equation. So I could write 0 equals capital F of x and y, which is just saying that this side of the equation is an expression in both x and y. It has x's and y's in it. And we use this capital F. So when you see this notation here, this is essentially just describing an implicit form of a single variable function. We can then drop that over more into multivariables. So now we know that z equals f of xy. Right? Z is a function of f of xy, and that's explicit. But I can do the same thing by dropping the z to the other side, 0, subtract it over to the other side, and say, okay, this here is a function of, or an expression in 3 variables. So I could write it as capital F of x, y, and z. It's got 3 variables in it, x, y's, and z's. Now, if you go back and say, all right, let's look at that previous example. And in the previous example, we had, fx times x minus a plus fy times y minus b, and we had the function value. But as far as this piece here, we had fx times x, fy times y, and then we had the z over here, right, with the function value being part of this as well. Let's say ab. And then after we plugged everything in, we distributed here, and grouped everything together. Well, I grouped some stuff to the left-hand side. I could have easily just grouped over to the right-hand side. But we got to this plane that was, in our general form, which is ax plus by plus c equals d, where the a was fx, the b was fy, and the cz, I should say, I forgot the z there, was what? Well, it was, if you bring this over, it was negative 1 z. In which case you look at it and go, okay, well, what is that? If this coefficient is the derivative with respect to x, and this coefficient is the derivative with respect to y, we really could think of this coefficient here as a derivative with respect to z. Because if I look at it in implicit form, and I say, let's take the derivative of this with respect to z, this whole piece would be 0, because x's and y's are treated like constants, and the derivative of z would be negative 1. So this idea of thinking about this as a function of 3 variables isn't that unusual. But nonetheless, this doesn't really matter. We're just trying to relate it to what we just did, in that, first off, just understanding if this is the implicit form of a 2-variable function. So then we go over and start looking at the equations of planes for implicit. So let's say we have this implicit function, fx, y, z equals 0. So we got an implicit equation. not an explicit but an implicit equation, and we want to find the equation of the tangent plane or even the normal line. Well, we can do that. We could even use this implicit form for a tangent plane and a normal line if we were using an explicit function, because we could just set it equal to 0 and do the same thing again. But anyway, what it says is that we should do capital Fx times x minus x sub 0, where the point in question is x sub 0, y sub 0, 0 sub 0. The partial with respect to y times y minus y sub 0. The partial with respect to z times z minus z sub 0 equals 0, which is basically saying that the normal vector to the plane is fx, fy, fz, because that's the coefficients in my plane. And if that's the normal vector to the plane, then we can talk about writing the equation of the normal line by using, this should be capital F. This should be capital F. And this should be capital F. By using the vector that's perpendicular or normal to the plane, and our line there, and therefore the normal line would be parallel to that, and we can place it in our normal line equation, where x sub 0, y sub 0, z sub 0 are all points, part of a point that we're going through. These are the components of the vector, and we write the equation of our line. Now, like I said a second ago, this is no different than what we've been doing. The equation of the plane is really the same. This is the same thing as what we had a second ago, fx at AB times x minus a. I'm using x sub 0 instead of a, but this is really used to be a, this used to be b just a second ago, and z was f of AB. Okay? So you notice it's really not that different than what we were seeing before. So this first piece is really this times x minus a. This piece right here is fy at AB times y minus b. Again, same thing, just using different notation. And then this last one, like I said, that f of z is really -1 a second ago. When you're in explicit form, again, this form, fz is -1, which is really this derivative moved to the other side. So the formula I'm giving you is not really new. It's the one we've been dealing with this whole lesson. So well, let's do this question. I think it might be a little bit clearer. So here's the function we're trying to find the tangent plane and normal line to. This is the surface, I should say. And that surface is in implicit form, not explicit form. So what I'm going to do is first put it into proper implicit form, which is to set it equal to 0. So I got to move the 3 over. Now the fact that it's a constant doesn't really make that big of a difference, because when I do my derivatives it's going to be 0 anyway. But if this was something that had variables in it, it would definitely make a difference to move it to the other side. So now what we're going to do is we're going to call this capital F. That's capital F of x, y, z, and it's equal to 0. So I'm going to find the partial of capital F with respect to x, the partial of capital F with respect to y, and the partial of capital F with respect to z. Which is not hard to do here. If I do it with respect to x, I'm going to get 1/2 x. If I do it with respect to y, I'm going to get 2y. If I do it with respect to z, I'm going to get 2/9 z. Then what I'm going to do is I'm going to evaluate each of these at the location. where we're trying to find the tangent plane. So -2, 1, -3. In which case, I'm going to get, say, -1, 2, and -6/9, so -2/3. Okay? And then I'm just going to plug them into here and here. So this is my x sub 0, y sub 0, z sub 0. These three pieces are going to go here, here, and here. And so the equation of the tangent plane will be -1 times x minus -2, so x plus 2. This is a -1, let's make that clear, -1, plus 2 times y minus 1, and that's this here, and then y here. And then -2/3 times z minus -3, so plus 3, equals 0. So there's the equation of the plane. Already in general form of what a plane should look like. If you wanted to put standard form, we could distribute out these parentheses, but it's fine to leave it like that. And then we got normal line. And so normal line, we have to have the vector that's normal to the plane, which this is the components of that vector right here, because they are here, here, and here. And then we need the point, which is this, and so we get x equals -2 minus 1t, y equals 1 plus 2t, and z equals -3 minus 2/3 t. And so that's the parametric equations for a normal line to the plane. Now let me just take this one step further. Let's say I had an explicit function. Let's say I had z equals x squared plus 3y squared minus 2xy. I could use these formulas to find the equation of the tangent plane for this. But I would first put this in implicit form, which would just be bringing the z over. And so I would get 0 equals x squared plus 3y squared minus 2xy minus z. And if you see, what do I get for f and z? I would get -1. So whenever you have an explicit function, this component is always going to end up being -1. But when you have an implicit surface, that's not necessarily the case. But you can still use this formula for the tangent plane and the normal line. Just remember that this should be capital F. It's the implicit function that we're working with, not the original function. Okay?